So let's start. Uh, so in the last class, we started looking at how to solve convex optimization problems, right? Constrained convex optimization problems. If if the problem given to us is unconstrained, then all we have to do is just find the gradient, set it to 0, and uh, and that gives us a solution, right? This is of course if we are looking for closed form solutions for differentiable convex optimization, convex functions. But if we have constraints, then it's not clear what needs to be done, right? So towards that, I given any convex optimization problem in standard form, such as we want to minimize some function f0 of x subject to a bunch of inequality and equality constraints. What we did was I defined this new function which I call the Lagrangian. So it's a function of not just x but also two new sets of variables, what we call the Lagrange multipliers, and it's basically a function which includes the constraints as well, right? So for every single inequality and equality constraint, I introduce a Lagrange multiplier. So the Lagrangian is a linear function of the Lagrange multipliers, but ultimately it involves all the functions in question, right? And given this quantity, if we look at the infimum of the Lagrangian over all possible x in the domain, then this gives us a function which involves only the Lagrange multipliers, and this is what we call the Lagrange dual function. All right, and since the Lagrangian is linear in lambda and v, and the Lagrange dual function is obtained by taking the infimum over all possible x. So it's an infimum of linear functions. We can say that g of lambda comma v is concave, right? So irrespective of whether f0 or any of the fi's were convex or not, the Lagrange dual function is always guaranteed to be a concave function in the Lagrange multipliers, right? And the other property that we saw was that suppose we're interested in minimizing f0 subject to those constraints, then the Lagrange dual function is always a lower bound on the optimum value. So let's call the optimum value p star, then g of lambda comma v is always less than or equal to p star for all possible combinations of lambda comma v with lambda greater than or equal to 0, component wise greater than or equal to 0, right? Any questions? Right, so these were two basic properties that we saw. One is that the Lagrange dual function is always concave. The second, that's always a lower bound for the optimum value. Now, of course, the only assumptions that we've made up to this point are that the problem is feasible. This minimization, there exists at least one point x which satisfies all of these constraints. That's it. All right. So this property that the Lagrange dual function is always a lower bound for the true optimum is what is called weak duality. So given the original problem, what we'll also call the primal problem, which is you minimize f0 of x subject to a bunch of inequality constraints and equality constraints. right? So this is what we call the primal problem. Now, corresponding to this, we define the Lagrange dual function, and as we know, the dual function is always concave, right? So we can look at another problem, which I call the dual problem, which is to maximize g of lambda v subject to the constraint that lambda is component wise greater than or equal to 0. All right. So let's say that for this, the optimum value is p star. And let us say that the optimum value for this problem is, let's call it d star. Since we know that the Lagrange dual function is always less than or equal to p star subject to this constraint, the optimum value should also be less than or equal to p star. Right? So this is what we call weak duality. And the utility of these two different ways of looking at the same problem is that sometimes the dual problem can be easier to solve, right? Because after all, we have fewer constraints. In this case, these constraints can be pretty complicated. Whereas in this case, it's a simple case, it's much simpler. And moreover, if you had only equality constraints, right? If there were no fi of x less than or equal to 0, then it would just be a maximization problem of g of v subject to no constraint. It's an unconstrained maximization problem, which we know very well how to solve. All right, so just to understand this better, let's perhaps take a look at some examples. Right, so in the previous class, we took one particular example where f0 of x was x transpose x. So the goal is to maximize the squared norm or the norm itself. Minimize the squared norm subject to some linear equality constraints, right? Some linear constraints. Right? And in this case, we saw that the Lagrange dual function was equal to this particular quantity, minus 1/4 v transpose A transpose v minus v transpose b. So let's take a specific A and B. Right? Let's suppose that the problem is to minimize, say, x1 square plus x2 square. All right, just a problem in R2 subject to let's say x1 plus x2 equal to 1. Okay, so this is my f0 of x, and I have only one inequality constraint, which is x1 plus x2 minus 1 equals 0. What is the dual function? Yeah. Oh, no, not the Lagrangian, but not the, so I want the Lagrange dual function, which is obtained by minimizing over all possible x. So we already had a closed form expression, a general closed form expression in the last class. Minus v square by 2 plus yeah, I think it should be minus 3, right? Right. Okay, so let's try to plot these functions and see what they look like. Uh, minus 1 to two. Let me call this f0, which is x1 square plus x2 square, and I also need a way to visualize the constraints. So it's over the set of all x1, x2 such that x1 plus x2 equal to 1. So x1 plus x2 equal to 1, or x2 is equal to x1 minus x1. Let's see what this looks like. Right, so this is what the function looks like. The blue colored surface, that's x, right? But we're only interested in those x1, x2 which satisfy a particular constraint, right? It's like taking a slice of that particular function. Let me change. Right, so you're taking a slice of this particular function. So the set of constraints just defines a line in this particular case. So ultimately what you're minimizing is some convex function in one dimension when you restrict to these particular constraints, right? And you can think of this even analytically, right? So I have this specific constraint of x1 plus x2 equal to 1, right? So what does the problem reduce to? So you know that x1 plus x2 equal to 1, that's the only constraint you have. So x2 equal to 1 minus x1. So effectively what you have is you just want to minimize x1 square plus 1 minus x1 the whole square, right? So let's look at that. And what is the minimum value equal to?
1 by 2.
Half, right? X. So let's say that I take x equal to equal to x square plus 1 minus x whole square, and I'll also plot the dual function. So what is the dual function equal to? It's minus v square over 2 minus v. So if I had to maximize this, what would the maximum value be equal to? So let's maximize minus v square by 2 minus v. So in this case, what is p? So what is p star equal to? Half. And if I want to maximize minus v square by 2 minus v, so d star is also equal to half. Let's look at this. So v, and at what point is the maximum achieved? Minus 1. Right, so I'll just plot these two functions. So this is, I should have turned on the grid. Right, so the function that we wanted to minimize, the primal function, is actually this blue curve. This is when subjected to the constraint that x1 plus x2 equal to 1. But on the other hand, if I plot the dual function is always a lower bound to p star. Right? So it's going to be less than or equal to the primal function itself. But in this particular case, it so happened that p star is equal to d star. So what we were able to prove was that d star is always less than or equal to p star. The maximum of the Lagrange dual function is always less than or equal to the optimum value of, or the minimum value of the function subject to the constraints. Correct? But in this case, what is nice is that d star is equal to p star. Right? So let's see some more examples to see if this is always true. Yes.
What was y1, y2, y3 in the...
It was just something that I just wanted to plot the constraints. All right. Effectively, what I want to plot is the hyperplane which corresponds to x1 plus x2 equal to 1. Set of all x1, x2, y for which x1 plus x2 is equal to 1.
So, in the course, G would be infimum, right? Infimum of x naught.
So this should be infimum. That's correct. So ultimately, we'll be taking the supremum of G over all possibility. Yeah.
Star equal to open, star equal to all.
Which, so that's it. I mean, I have plotted both of these in one plot, but so it's a little bit misleading because the variables involved are different, right? Because this is a different variable. These are the Lagrange dual variables, right? The Lagrange multipliers. The V is a Lagrange multiplier, whereas this is the problem which corresponds to the primal variables. And in this particular case, it so happened that these two are of the same dimension, but in general, it may not be the case because the dimensionality of V depends on how many equality constraints you have, not on whether the dimension of the original problem. If f can be from a function from Rn to R, and maybe you have one equality constraint. So subject to the equality constraint, the original problem is an n-1 dimensional optimization problem, whereas the dual problem is just a one-dimensional optimization. So that's another reason why the dual problem can sometimes be easier to solve, because if you don't have too many constraints, then you're looking at a problem of a much smaller dimension than the original one. Of course, you have to compute the Lagrange dual function. That's a separate issue, but sometimes you can. Okay. So let's see another example, sort of a almost trivial example. Let us take f of x equal to, let's say, x cubed. Okay, and subject to some constraint. So I want to minimize f of x equal to x cubed, subject to the constraint maybe x is greater than or equal to 1. Right? So minimize f of x equal to x cubed subject to x greater than or equal to 1. Right? So I have one inequality constraint, the same as saying minus x plus 1 is less than or equal to 0. So what is the Lagrangian equal to? So it's f of x cube plus lambda times the constraint minus x plus 1. And what is the infimum going to be equal to? Yeah? Root lambda, why is that true? So it's the infimum of over all possible x of x cube plus lambda minus x plus 1. Sorry? It's infimum. It's g of lambda. Let's go back to the definition of g. So g is basically the infimum over all possible x in the domain of the Lagrangian. So it's an unconstrained minimization problem. Yes, what is this equal? Minus infinity for all lambda? For all lambdas? Lambda, fine, you can look at g of lambda for all possible lambda. So it's always minus infinity. So this is certainly a lower bound to our optimization problem, but it gives a trivial, useless lower bound. Correct? But of course, this function to begin with was not a convex optimization problem. X cube is not convex. Correct? But that doesn't mean that this approach will not work. So irrespective of whether f is convex or not, you're guaranteed to get a solution. Sorry? In the constraint set, x cube is convex. Fine. So correct. So let's now look at the redefinition of f of x. Okay. Okay, so in what region is f of x convex? 0 to infinity. Great. So let's say that f of x is equal to x cubed for x greater than or equal to 0, and let's say it's minus infinity for it's plus infinity for x less than 0. Okay. Right, so now let's look at the same problem. So L of x lambda is just f of x plus lambda times, what was it that we had, minus x plus 1. Now what is g of lambda equal to? So firstly, can the infimum ever be achieved for any x less than 0? No, right? Because L of x lambda is equal to infinity for x less than 0. This is equal to x cubed plus lambda times minus x plus 1 if x is greater than or equal to 0, and it's equal to plus infinity if x is less than 0. Okay, so what is this infimum equal to in that case? Suppose lambda is positive or non-negative. So x is
They're not a max.
So is x cubed plus lambda times minus x plus 1 always convex in your domain? For x greater than 0, x cube is convex. Yeah. What about x cube what is this? Is going to be x cube minus lambda x plus lambda. Sorry. Yes. Okay. So that is if lambda is greater than or equal to 0. Which one? Fine. The second derivative is always going to be 6x. Yes. Okay. So what is the minimum infimum equal to? Yeah. Lambda minus 2 lambda by 3. Root lambda by 3. Can you tell me once again? So it's equal to lambda times 1 minus 2 by 3 root lambda by 3. Right, so what is supremum for all lambda greater than or equal to 0? G of lambda. Supremum. So maybe just to visualize, let's plot these two functions. Right, so this is what the function looks like. Maybe I should have plotted it for something more extended value. Right, so this is the original function that we were trying to minimize, subject to a constraint that x is greater than or equal to 1. So really, what is the minimum value? it's equal to 1. That's an almost trivial problem. And this is what the dual function looks like. The Lagrange dual function. It's a concave function which achieves maximum of 1. Right? But of course, you can also try to solve this maximization problem on your own. Try to differentiate this, set it to equal to 0, and you'll get lambda equal to whatever, something 3. Yeah. So you take lambda equal to 3. This becomes 1 minus 2 by 3 into 3, so that becomes 1. Can you the only in the region where the constraints are satisfied, right? So all we are saying is that the Lagrange dual function is less than or equal to P star, right? So it's only subject to those constraints. So to take this particular example, the dual function is crossing over with the primal function. But if you look at the primal function only in the region where the constraints are satisfied, which is basically to the right of 1, so this is really the function, the dual function is always less than or equal to this. And really there's no way to compare the two directly because the variables involved are different. They're not functions of the same variable. That's something that you always have to keep in mind. Correct, good question. I'll get to that in a little bit. So we say that strong duality holds if basically P star is equal to D star.
Where the constraints hold, like the entire region of where the constraints hold, the dual is always the
Yes, because the dual function is always less than or equal to P star, which is the minimum value of the function anyhow, so it should be less than or equal to the function. So given a particular optimization problem, we say that weak duality holds for this optimization problem if D star is less than or equal to P star. And we say that strong duality holds if D star equals P star. Right? Let's suppose that strong duality holds. We're still not sure when strong duality will hold, but suppose that it holds. Then how do we solve the optimization problem? Or what does the optimization problem effectively reduce to? So suppose that strong duality holds. Then we can find the optimum value by, so we're given an original constrained optimization problem. What we can now do is, so P star is equal to D star, which is equal to the supremum over all possible lambda greater than or equal to 0 and over all possible V of G of lambda P. Right, but this is equal to the supremum over all lambda greater than or equal to 0 over all possible V of the infimum over all possible X of L of X comma lambda comma V. And what do we know about the function L? Right? So L is, let's suppose that L is convex in X. Suppose that all the functions under consideration are convex. That makes sure that L is convex in X and concave in lambda and V. Then effectively what we are trying to do is finding a max min of some particular function, which is equivalent to finding the saddle point of a particular function. So really this approach, wherever strong duality holds, is one of finding the saddle point of a given function of the Lagrangian. Right? So in fact, let's take another almost trivial example of f of x equal to x square, subject to the constraint x is greater than or equal to 1. So L of x lambda would be equal to x square plus lambda times minus x plus 1. Okay. So let's plot this function with respect to both x and lambda. Square plus L times minus x plus 1. So really this is what the function would look like. So it's right, so as you can see, it looks like a saddle. Right, and the problem effectively boils down to finding the right saddle point. right? But of course, we're not sure when this property holds. So all of this is under the assumption that strong duality holds. But even if strong duality does not hold, I can still try to solve this saddle point problem and at least get a lower bound on the minimum value. Right? That's something that is always doable. So this is always doable. And remember, so far I've made no other assumptions on f, right? Even if f is non-convex, the constraints are non-convex, I can still get a lower bound using this by solving this dual problem. So of course, if you had to guess when strong duality holds, what would be your best? Okay, f. Okay, so f is convex. Do you think that's a sufficient condition for strong duality to hold? Sure. So a convex optimization problem. So it turns out that that's not sufficient. There's another property that is required, and we'll see that in a while. So let's take another example.
Yes, some convex functions.
Which one?
If you have f as convex,
Okay.
and the constraint sets are convex,
Okay.
that is only Lagrangian automatically become a sum of convex functions.
Okay. So
that is.
So again, the point is not whether it's a convex optimization problem, right? The question is this D star? The D star is obtained by solving a maximization problem of some function, and P star is obtained by solving a constrained minimization problem. It is not obvious as to why these two should coincide at all. Okay. But somehow for a very large class of convex optimization problems, this happens to be the case.
When you're summing them up, when you get the Lagrange function, when
Okay.
you them up,
Yeah.
you essentially have the intersection of all the minima individually, right? Like if you're minimizing it.
I'm not sure.
Okay, not.
This is a weird looking function.
Does the additional condition have anything to do with conjugate function?
No.
So why did we learn about that?
We'll see that. We'll see. In fact, the Lagrange dual function itself can be expressed as a conjugate of some function. Right? So, but before that, let's just take one particular example. So let me say that f of x is equal to e to the minus x for x. Okay, so it's going to be a function in two variables, x comma y, for x greater than or equal to 0 and in fact x in R, and y strictly greater than 0 and infinity otherwise. Okay, so it's really a function of e to the minus x, but there's also this change happening when y is greater than 0 and y is not greater. Okay. I want to minimize this subject to the constraint that x square by y is less than or equal to 0. Yeah, so yeah, y has to be greater than 0, of course. So really, what is the solution to this problem? Huh? X is in R. But is there a feasible point, firstly? Yeah, there's one feasible point. Actually, there are infinitely many feasible points. Take x equal to 0 and any y greater than 0. Okay? So there are infinitely many feasible points. And what is the minimum value of f of x comma y? 1. Right? So for this problem, p star equals 1. Yeah. Sorry? That's fine. So the whole problem is defined for fine. So you can say x 0 comma y, where y is greater than 0. Okay. Correct. Sure. Okay, fine. So let me add the additional constraint that y is greater than or equal to 0. X. So since the domain is in x r comma r plus, the constraint set, when you take the intersection with the domain of the function, that just turns out to be set of all 0 comma y greater than 0. Which, fine, or I can say that this, okay, let me say that this for x in R, y greater than 0. So that's the domain of the function.
No, like, I mean, like, even if we don't have y greater than or equal to 0, everywhere else is going to be infinity. So
correct.
This is going to be 1 anyway, like, even if we don't have y greater than.
Sure, okay, fine. However you want to take this. Okay. Okay, so the only point that I'm trying to make here is that the constraint set is convex. Yeah?
Y should be less than.
So let me eliminate.
No, in the constraint.
In the constraint set,
Y should be less than equal.
y, so irrespective of what value of y I choose, this always satisfies the constraint. Okay, so for this problem, what is the Lagrangian? Lambda, this is equal to f of xy plus lambda times x square by y, which is equal to e to the minus x plus lambda times x square by y if x is in R and y is greater than 0, and it's equal to infinity if y is less than or equal to. What is g of lambda equal to?
Just lambda greater than 0.
Fine, lambda. You can find g of lambda for both lambda greater than or equal to 0 and less than 0. And you'll see that they take different values.
Greater than or equal to 0 is 0.
Yeah. So g of lambda is infimum over all possible x y L of x y lambda. So if lambda is greater than or equal to 0, then what is the minimum value? If lambda is greater than or equal to 0, then certainly this quantity for y greater than 0, this quantity is always greater than or equal to 0. Right? And does it approach 0 at some point? No. If lambda is greater than 0, as you let x to tend to infinity, what happens? It tends to infinity, sorry. What happens when you let x to tend to 0? What kind of function is this? What is the infimum equal to? Yeah? 1. Right? So if lambda is greater than or equal to 0, then what is the infimum equal to? 1. Okay. So check once again. So it's the infimum over all possible x and y, right? Yeah? Yes. So it tends to 0, and how y does it tend to 0? So you let y to tend to infinity at a rate faster than x, right? So for example, if I take y equal to x cube and let x to tend to infinity, then what does this tend to? Right? So g of lambda equal to 0 when lambda is greater than or equal to 0. If lambda is less than 0, what happens? So if lambda is less than 0, then there's some choice of x and y, for which you can take, for example, you take any positive value of y, let x to tend to infinity. This whole quantity tends to minus infinity. So in this case, what is d star equal to? It's 0. It's the maximum value of g of lambda. So this is equal to 0. But what was p star equal to? 1.
So Isn't G of lambda infinite and y is less than or equal to 0?
When, sorry, what?
When y is less than or equal to 0,
When
G of lambda
y?
infinite.
Okay, so y is less than or equal to 0.
Because f of x y is infinite.
No, I'm not sure I follow. So g of lambda is this, right?
So when y is less than or equal to 0,
Okay,
f of x y is infinite, right?
okay.
So then won't G of lambda also be infinite when y is less than or equal to 0?
No, right? You're taking the infimum over all possible x and y.
Oh,
There's no
Yeah.
y left over. So this is an example where weak duality holds. And strong duality does not hold. So we'll specifically look at cases when strong duality holds, but just to give a preview of when it holds under two conditions. One, that is the function involved is convex. The second, when you can find a point for which the inequality constraints are not satisfied with equality. Right? It's a weird looking condition.
So, but do we not require the convex constraints have to be convex?
No. So we'll see this in more detail later, but we'll see that strong duality holds if, again, it's a sufficient condition. So it holds if f is convex and there's at least one point in the domain, in fact in the relative interior of the domain, such that fi of x is strictly less than 0 for all I and hi of x equal to 0 for all.
So why can't it belong on the board?
Which
X.
we'll see that a bit later.
How does this imply that?
It doesn't, no, I'm not saying that this implies that strong duality holds. I'm saying that this happens. We'll see why it happens later. Yeah.
I'm asking that the previous statement you had said was
Yeah.
that when the inequality cannot be satisfied with an equality, right?
Correct. So basically, fi of x is not satisfied with equality here. It's strictly, so there's some point which is for which it's a strict inequality. All the inequality constraints are satisfied with strict inequality. Okay.
And the H1 is just a standard condition.
It's just, yeah.
Did we make that less than because of relative interior?
Not necessary. There could be a point in the relative interior for which it's satisfied with equality also.
So you could technically decompose one into y and minus s.
We,
Like my
okay.
suppose there's an sk, we can decompose it into minus sk less than equal to 0 plus sk less than equal to 0. there, it won't hold.
It won't hold. So that's one reason why we are separating out the inequality constraints and the equality constraints.
Can we compose the like less than equal to as a separate h equal to?
What do you mean as a
Like
separate?
for example, if you have fi of x less than equal to 0 is there.
Yes.
You write it as two different functions where fi is less than 0 and hi is equal to 0, and both will be satisfied for the same x.
Sorry, fi is less than
So
0.
say okay, you have some fi
Okay.
fi of x less than equal to 0
Okay.
that is satisfied for some x.
Okay.
That can be decomposed as two different functions, right? So you have say fj of x less than 0 and some hj of x equal to 0.
But does it give the same problem?
Right. Give us some problem.
So if there's a point that satisfies f I of x equal to 0, so you want to decompose fi as you want to write fi of x less than or equal to 0 as two constraints, you're saying.
One is fj
One, fine, let's call f bar of x
less
less than 0,
and h bar of x equal to 0.
h bar of x equal to 0. Why do these two combined together correspond to this constraint?
That is really not intersection.
Yeah, it's intersection, right? Not union. So you cannot decompose this as these two. So now let's look at the dual function once again. So we have g of lambda v to be equal to the infimum of f0 of x plus lambda summation over I lambda I fi of x plus summation over j vi hi of x. Let's now assume that both these fi and hi's are linear constraints. Okay, so let's look at a problem where we want to minimize f0 of x subject to some constraints. Let's say a x less than or equal to b and c times x equals d. This is the same as saying ax minus b is less than or equal to 0 and cx minus d equals 0. So what is g of lambda v equal to in this case? Right, so each fi of x is basically some ai transpose x equal to bi or ai transpose x minus bi, right? And I can basically write this quantity as lambda transpose ax minus b and this quantity as v transpose cx minus d, right? Okay, there are some terms over here which don't really involve x, so I'll just take them out. So it's the infimum. Let me take the other terms out. So I have minus lambda transpose B minus V transpose D plus infimum of f0 of x plus lambda transpose AX plus V transpose CX. Okay, but this is also equal to the transpose B minus V transpose D plus infimum of f0 of x plus, I'll write this as x transpose A transpose lambda plus C transpose V. Right, I can write that. Okay. This is also equal to minus lambda transpose B minus V transpose D plus, I'll take a negative over here and also a negative inside. So basically what I get is minus a supremum of x transpose A transpose lambda plus C transpose V minus f0 of x. I'm doing nothing else here but just manipulating the same quantity. Right, so this is my G of lambda V. Does this look familiar? Yep, so this is minus lambda transpose B minus V transpose D minus, let me write this as supremum over all x of x transpose of minus A transpose lambda minus C transpose V minus f0 of x. Yes. So it's equal to what? It's what conjugate? F star of minus A transpose lambda minus C transpose V. And what properties do we know about the conjugate of a function? Yeah, it's always convex, correct? So minus the negative of the conjugate is always guaranteed to be concave, plus what remains is just a linear function So this is always going to be a concave. So as long as you have any function for which you know the conjugate, finding the dual is pretty easy. The Lagrange dual is very easy because it can be expressed in terms of the conjugate evaluated at a certain point plus some kind of a shift.
We see this form only when our constraints are like linear, or
Yep.
like we also see the conjugate come out given the constraints and context.
So let's suppose that you just take some other convex constraint. Effectively, what you would have is f0 plus you would have a lambda transpose some nonlinear function of it. So that's not in the form of the conjugate of. Right? So in general, the answer is no. But in the special case where all your constraints are linear, fine. The dual function effectively boils down to the conjugate of the original primal function. Right. So let's stop here. Any questions? Yeah. Yes. It's infinite. Correct. Yeah. So if you look at just the constraints, then yes, right?